So here's what we have. What is EigenStuff? We view the matrix A as a linear transformation, right? You remember from last time, I have a 2x2 matrix, right? And I apply it to a 2x2 vector, out comes a 2x2 vector. So here's a vector A, it comes out B, something like that. So here's a vector X. To that X, I'm applying the transformation A. So this is the input space of A. So I'm computing AX, and AX ends up being this. In general, when you apply the transformation A to a vector, that vector changes direction. In this picture, both vectors X and Y, when A is applied to them, they change direction. X pointed this way, AX points that way. It's not on the same line. Y pointed that way. When you applied A to Y, it's some two-dimensional vector, again, lives in a two-dimensional plane. The input space is a plane. The output space is a plane. Those guys point in separate directions. You can take those two spaces and put them on the same, have the axes coincide. Okay, just put all the vectors here on the same plane. So here was my original X. When I applied A to it, AX is what I ended up with. Points in a separate direction. But what if, you ask? Yes, those guys point in separate directions, but what if there is a vector to which, when you apply A, that vector doesn't point every which way. It stays on the same line. It may change direction, but stays on the same line. For example, what if there is a vector like this guy V here, this guy V? Apparently, when I applied A to this V, A of V stayed on the same line. In fact, it was stretched twice, right? If you can find those kinds of special vectors that are kind of A's own vectors, they're called eigenvectors, that don't change direction when A is applied to them. Those special vectors are called eigenvectors to A. And the stretch factor, the amount by which you get to stretch the vector that stays on its own line, that amount is called an eigenvalue. Okay, that 2, for example, is an eigenvalue for the eigenvector V. Why is V an eigenvector? Because when I applied A to this vector V, that vector V didn't go this way or that way. It stayed on the same line, That's why it's an eigen. That's what it means for a vector to be an eigenvector. And again, the stretch factor is an eigenvalue. So from now on, this is the way we'll think about eigenvectors and eigenvalues. And of course, you may be asking, so good. So what's the point? Well, as it turns out, it has many, many applications. One of which is to efficiently compute the powers of a matrix, the need for which we discussed briefly at the start of today. So let's do a couple of examples to make sure that we're all on the same page before moving on. So here's an example. Here's A. That's one particular A. It's a 2x2 matrix. It is a transformation from a two-dimensional space to a two-dimensional space. Which two-dimensional? Well, I can have those two pictures of these two-dimensional spaces, which are planes coinciding. I could draw them all in the same plane, but let's draw them separately. So here's the input space of A. These are the vectors that go in, that are in the domain of A. You apply A to them. Let's take this vector, 1, 1 vector. So what happens when you apply this transformation to a 1, 1 vector? So what do I mean when I apply the transformation to 1, 1 vector? Well, you multiply that vector, 1, 1, by a matrix from the left. You're applying that transformation, which is represented by this matrix, to this vector 1, 1. What comes out on the other side? We know how to multiply a matrix by a vector, so that's not a big deal. So we're going to end up with 4 times 1 minus 5 times 1. So that's going to be minus 1. 2 times 1 minus 3 times 1. That's going to be minus 1. Minus 1. Is this a multiple of vector? So V was the vector that went in. Okay, so I'm applying. So this is my A. I applied that to the vector V, which is 1, 1 that went in. And out comes what? Does a multiple of V come out on the other side? Right? Yes, it's a multiple. It's minus 1 times V. This is the V vector is 1, 1. So apparently when this vector right here, this green vector went in, out came, it just flipped its direction. That's an eigenvector. It stayed on the same line. 1, 1 and minus 1 are collinear. Collinear means they're on the same line. Okay, they either point in the same direction or in completely opposite directions. It's a 180-degree flip here, this vector. How about the other guy? How about this vector? 5/2, 1. Let's see where that guy goes. So now this second example, I still have my A. And now I'm applying this A to, let's take 5/2 vector. Let's take vector 5/2. What happens if I apply this to vector 5/2? Please help me out. What's the output? So this is my vector V. This is my vector V. This is my transformation A. I'm applying A to vector V. Two-dimensional vector goes in, two-dimensional vector comes out. Again, thinking of A as a transformation, it's a function. Well, what's the result of transforming 5/2 with this linear transformation? Well, apparently, given our multiplication rules, it's 4 times 5 minus 5 times 2. That's 20 minus 10. That's apparently 10. 2 times 5 minus 3 times 2. 2 times 5, that's going to be 10. Minus 3 times 2 is minus 6. That's going to be 4. So that's 10, 4. So when I applied this transformation to 5/2, what came out of the other side? On the other side, does that vector, the red vector that I just wrote here, does this point in a different direction from 5/2, or do they both of these point in the same direction? These two vectors. Do they point in the same direction? Please help me out. I'm kind of lost.
Yes.
Sorry, one more time.
Yes.
Yeah, they point in the same direction, right? It's twice the original vector. So in went 5/2, and out came twice 5/2. So they point in exactly the same direction. So here is 5/2. Well, it's like half, 5 half. So here's 5/2 was going to be here, and out came 10, 4. These two red vectors here point in the same direction. Now, how about not 5/2, but 10, 4? If 10, 4 went in, what would come out on the other side? If this were 10, 4, out would come out 28. But it's still twice 10, 4. The point is that that vector, any vector in this line, is stretched twice. That 2 is the stretch factor of any vector in that line. Take a vector that points that way, still stretch 2 times. So that 2, that stretch factor, is the eigenvalue for the eigenvector. Which eigenvector? Any of the eigenvectors that lay in this line. Okay. In fact, I have an infinite number of eigenvectors. Any vector in that line is an eigenvector. Normally, when we haven't yet discussed how to find these things, the eigenvalues and eigenvectors, we'll discuss them soon. But once you find one eigenvector, so you just have to pick one convenient eigenvector. You'll normally have an infinite, not normal, you always have an infinite number of eigenvectors associated with a given eigenvalue, always. So people normally pick something that's convenient. So we'll pick these two guys here. Now notice that any vector that doesn't, well, that needs proof, but any vector that's not on any of these green lines, any vector not on these green lines is going to change direction, is not going to be an eigenvector. For example, the gray vector here, this gray vector, when you apply A to it, you end up right here. Okay, you can check this. So this guy was pointing this way, and now it's in a completely different line. Okay, the gray vector changed direction. That's not an eigenvector. So again, eigenvectors are the vectors that don't change. Well, they can change, if they change direction, they change direction in completely opposite direction. So the eigenvectors are those, the eigenvectors stay on the same line. Okay, stay on the line that they were on to begin with before they were being transformed by A. Okay, any questions about this general overview, what eigenvalues, eigenvectors are? Now, of course, okay, so now let's see where this may become useful. So how about computing? Okay, let me ask you this first. What is A squared V? What am I saying when I write down A squared V? What is that? So suppose V now is an eigenvector. That means that's one of those vectors that stays put on its own line. So when I say A squared, that means I'm applying A to AV, right? That's what it means. So shorthand A squared is that. Now, I know that A applied to V is going to be twice V because, because V is an eigenvector. So when I apply A to it, it stays on the same line. So it's stretched twice. Now, when we began this course, we had this boring set of rules. Multiply by the matrix by a constant. This is just a constant times like every entry of the matrix. Blah, 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 blah. And it's understandable that people thought, okay, so I see all these rules, so what's the point? Okay, so I get it, but not very exciting. And I completely agree with you that that's not very exciting. But those rules come in play when more exciting stuff happens. We're not quite there yet, but let's take a look at this. When I multiply A by 2V, one of those rules said that I can take 2 out. It's 2 times AV. That's what one of those rules said. And what is AV again? Now I'm justified to write this down as 2 times 2V because A applied to V is twice, it stretches the vector twice. So it's really 2 squared V. So notice what's happening here. When I applied my transformation, linear transformation twice to a given vector, then I don't really have to compute the square of that matrix. I really have no need. If I just want to know the effect of this matrix, a square matrix, and this given vector V, I simply can multiply this vector by a number, just by 4, not by the entire matrix A squared to see where that vector went under that transformation A squared. This pattern, of course, continues. If somebody has to prove this to you, you would do your proof by induction. But A cubed V, I think it's easy to see that this is, what is that? That's A applied to A squared V. And now you know what A squared V is. It's A applied to 2 squared V. Of course, you know that you can take the constant out, right? Here, and AV is going to be A squared times 2V. So again, so this is 2 cubed V, right? So instead of computing the cube of a matrix, you actually compute V multiplied by a number. That makes a huge difference computationally because computing the power of a matrix is expensive and computing just the power of a number, not expensive. Okay, so now it looks like I'm able to see the effect of the nth power of some matrix on a given vector. Why is this still useful? Well, in a very, very nice case, when you actually have it for a 2x2 matrix, if you have 2 linearly independent eigenvectors, then you're in complete luck. Now let's see why. First, let's remember what it means for 2 vectors to be linearly independent. Can somebody help me out? What does that mean? Although we'll stick with intuitive explanations, the way people understand that from reading assignments. So what does it mean? There is a formal definition we can get, but how do you understand linear independence of 2 vectors? So for example, in other courses, like in calculus or in physics or something, you wrote down what's called like a standard basis, so you have these 2 vectors, right? And you could express any vector, x1, x2, you can express as a linear combination of these 2 particularly nice vectors, right? So this one was 1, 0. This one was 0, 1 vector. And any vector x1, x2, like this vector, well, let's give it a red x1, x2, is going to be x1 times 1, 0 plus x2 times 0, 1. So any vector whatsoever on this plane, no matter what its coordinates are, x1 and x2, can be expressed as some mixture, and by mixture is our informal term for linear combination, as some mixture of those 2, these are called standard vectors. If you're taking, that could be in 3 dimensions. If you have 3 dimensions, you're going to have 0, 0, 1, 0, 1, 0, and 0, 0, 1, right? 1, 0, 0, 0, 1, 0, and 0, 0, 1, 3 vectors, IJK that you called in physics. Okay, so any vector in the 2-dimensional case or 3-dimensional space can be expressed as a linear combination of these 2 standard, these are called standard basis vectors. Okay, these are, we don't discuss angles in this course, but these are orthogonal vectors to one another, meaning that intuitively that are 90 degrees to each other. They're in fact what's called orthonormal bases, meaning they have length 1 and they're 90 degrees to each other. And of course, you can only imagine them up to 3 dimensions, but in general, there's nothing to prevent you from generalizing into 59 dimensions, right? Anyway, back to our question. These are nice standard vectors. If we have a notion of an angle, we would have called them orthonormal vectors, but we don't have a notion of an angle. My claim is here, so take these two vectors here, -2, 2, and 5, 1. They point, as we say, every which way. What does that mean? Well, they're not on the same line in 2 dimensions. They're not collinear vectors. When they point every which way, the claim is that any vector on that plane, like this red vector, for example, can be expressed as a linear combination, as a mixture, of these 2 blue vectors. So these 2 blue vectors, just like these vectors here, the standard vectors, I can take some amount of this vector, 5, 1, some amount of that vector, -2, 2, and add them up. And when I add them up, I get this red vector. And this is true not only for this red vector, but any vector on this plane is some linear combination of the 2 blue vectors. When that happens, what happens? When any vector on the plane can be expressed as a linear combination of some 2 vectors, those 2 vectors are said to form the basis in R2. These 2 vectors here, the blue vectors, form a basis in R2. Just as these 2 blue vectors form a basis in R2. They have a special standard name. These are called standard orthonormal bases. But these 2 blue vectors that are drawn here form a basis in R2. Now, that was a bit of an aside. How about when you get 2 eigenvectors that can form a basis? The example that we gave 2 seconds ago of a 2 by 2 matrix here, this matrix, this is a nice case. This guy, this matrix, has 2, they're shown in green here, 2 eigenvectors that point every which way on the 2-dimensional plane. That is, they are not collinear. One points that way, the other points that way. This means that these 2 green vectors can form a basis in R2. That means that any other vector on the plane can be represented as some linear combination of these 2 green vectors. Okay, when that happens, I can use these 2 basis vectors to compute the effect of applying any power of A to any vector in this 2-dimensional space. And that's where the usefulness of eigenvectors and eigenvalues kicks in. So let's talk about this for a second before we move on. So suppose you have a situation like the one we just described. You have a matrix A. That matrix A, suppose, has 2 eigenvectors. One of those eigenvectors is called V, the other guy is called W. And they correspond to these eigenvalues 2 and 7 respectively. That means that when I apply A to this vector V, I stretch it twice. When I apply A to this vector W, that guy gets stretched 7 times. So I have something like W, V, I apply A to it, I get this guy gets stretched twice, this guy gets stretched 7 times. But they stay in the same, the directions of those vectors do not change. Okay, now suppose that I want to compute the effect of applying the nth power of A to any vector X, not just to V or to W. I know what the effect of applying A to just W would be. I know what would that be? What would be A to the n W? What would that be? Please help me out.
7 to the n W.
7 to the n W, right? Just as just discussed. But because now W and V form the basis in R2, what does that mean? That means that any vector, this is an arbitrary vector X in the 2-dimensional space, is some linear combination of these 2 basis vectors. Then, well, first of all, when I apply A once to that vector, what comes out of it? Well, I have my arithmetic of dealing with matrix times number multiplications. This is what comes out of it. I apply A to it the second time. What comes out of it? A applied to this comes out of it. And that, as we just saw, is A2 squared times B plus B7 squared times W. So in general, when you apply the nth power of this matrix to X, and you want to know what the effect of this transformation is, you don't really need to compute the nth power of the matrix at all. All you have to do is know the basis of eigenvectors. And if you do know the basis of eigenvectors, you know the effect of this matrix's n power on any vector X whatsoever. No need for costly computations. All you need to do is compute the eigenvalues and eigenvectors. And then you know everything you need to know for many, 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 many applications. Okay? This works for nice matrices and that have n. Well, if they have, okay, so we'll talk about this. So just foreshadowing, I can tell you that if a matrix has n distinct eigenvalues, then this will always happen. You will always find n distinct eigenvectors. But you get even more lucky than that. Even if a matrix does not have, n by n matrix does not have n distinct eigenvalues, you can sometimes get even lucky, even in those cases, and find n distinct eigenvectors. And when you do find n linearly independent eigenvectors, and when you do find n linearly independent eigenvectors, the computation of the effect of the nth power of that matrix onto any vector X in the input space becomes a cinch. Very, very easy. Just this kind of computation. Okay, so now let's get to more to stricter definitions of what we mean by eigenvalues and eigenvectors. So here's a definition. Okay, yeah, you're given an n by n matrix, and we'll say that lambda is an eigenvalue of A if this thing happens here, right? Now, using lambda is a stretch factor. It's just a convention to use the Greek letter lambda here. You can call it anything you'd like, C, A, whatever, but lambda is the convention, and we're going to stick to it. So lambda, think of lambda as the stretch factor. That's all lambda is. So again, A is an n by n matrix. That n by n matrix is applied. What is V? What's the dimensions of V? What does V have to be? So V, again, it's a vector. So this is a matrix. So think of in terms of dimensions as always. So V is a column vector. In this notation is a column vector. Some people write down row vectors. We'll write down column vector. So V is a column vector, n by 1. Lambda is just a number like 5, 1/2, minus 22. And V, again, V is a column. So please keep in mind those dimensions. So in this case, what? We have 4. All right, 4. So A apparently here, the way I've drawn it, should be 4 by 4 matrix because the V is like 4 tall column vector. Okay. Okay, so we'll see all the uses of this. So now let's make sure that we're all on the same page before we move on. Is 2, 5 an eigenvector of the matrix 1, 2, 5, 4? So please help me out. So here's my matrix. 1, 2, 5, 4. Is 2, 5 an eigenvector? Okay, so why is that? So 1 times 2 plus 2 times 5, that's 12, right? That's 12. 5 times 2 plus 4 times 5, that's 30. Okay, why is this an eigenvector?
Because it's 6 times V.
Yeah, that's because it's 6 times V. So this blue vector, currently, that 2, 5 vector, or any multiple of it. Can you name any other eigenvector, please, in this space, in this 2-dimensional plane? So we're living now in this 2-dimensional plane. Our transformations go 2 by 2, right? Can somebody name just one more vector? Any? That's also an eigenvector.
410.
410, or even that 1230 is also an eigenvector, right? So yeah, anything that's a multiple of this blue vector is also an eigenvector, or points in the opposite direction. -4, -10 is also an eigenvector. -2, -5, an eigenvector, right? Why? Because when you apply A to it, it gets stretched 6 times, stays in the same line. So this is an eigenvector. Is 0, 7 an eigenvector? Okay, so 1, 2, 5, 4 applied to 0, 7 can that be an eigenvector? Well, first of all, I get something non-zero here in this position. In fact, I get 2 times 7, 0 plus 2 times 7. I get 14 in that position. But all I care about is to say this is non-zero. What do I get in this position? Well, you're going to say you get 28 in this position because it's 5 times 0 plus 4 times 7. But I'm simply going to say that this is non-zero. That's sufficient for me to make a claim I'm about to make. The claim is, because these two entries are non-zero entries, can this be an eigenvector? There's no way, right? Because 0, 7 is right here. 0, 7. I'm sorry, is right here. 0, 7. 0, 7, this vector. No, that's not true. But yeah, 0, 7 is right there. How about like any other vector? Take this vector, like x1, x2 vector that jets out from here. So this is 0, 7 vector here. And this is some other vector, x1, x2, whose entries are non-zero. I took 2 positive x1, x2 entries. Is there a way of stretching any the vector on this axis to get a vector on this line? There's no way. Therefore, 0, 7 cannot possibly be an eigenvector, right? For this transformation. So for this transformation. Therefore, 0, 7 is not an eigenvector. Okay. It's a good exercise to find, it's a good exercise to find a transformation for which a given vector would be an eigenvector. Now that's a good exercise, but let's leave that issue alone for a second. Okay, so now let me ask you this before we move on real quick. What is the 10th power of 2, 5? 10th power of A applied, what did I just say? 10th power of 2, 5? The 10th power of A applied to this eigenvector, 2, 5. So remember, 2, 5 is an eigenvector with eigenvalue 6. What happens when I apply the 10th power to it? The 10th power of the matrix. So remember.
It's 6. Okay.
Yeah, what is it, please?
It's 6 to the 10th times the vector.
Exactly, 6 to the 10th, this vector. So notice, all I have to do is know what 6 to the 10th is. That's much easier for a computer to do than compute the power of a matrix. How about this one? Remember that -1, 1 was an eigenvector whose lambda. So notice what we have, by the way, just looking ahead a little bit. For each eigenvector, for each eigenvalue, we have a corresponding eigenvector, which we have distinct eigenvalues here, and those eigenvectors point every which way. This will generally hold true every time. You get n by n matrix, you get n distinct eigenvalues as we have here. 6 and -1 were the two eigenvalues. Let's call them lambda 1 and lambda 2. For these two eigenvalues, we have two eigenvectors that point in different directions. One of those guys is 2, 5, and the other one is -1, 1. So you remember, right? So when we applied this to -1, 1, out came 1, -1, right? So that was -1 times -1, 1, right? That's what I mean. So it's lambda 2 is -1. That's a eigenvalue here, corresponding to this eigenvector, -1, 1. So notice the language. An eigenvector corresponding to an eigenvalue. We'll keep using that language. Okay, so what's the result of this?
It's a vector, -1, 1. Since -1 to the 10th is 1, so it's
exactly. So that happens to be -1, 1, because when I applied A once, I flipped the direction, got to -1, -1. When I applied A again, A squared, it flipped again. So I came back to the same vector from which I started. So every eventh application of A leaves me unchanged, leaves this vector unchanged. Every odd application of A flips its sign, its direction, 180 degrees. So that's, you can say it's -1 to the 10th power of that, right? So in general, if I have an n here, an n, like 2168, I get, oh, no, not here. Not here. This is a good exercise you should do. And I just discovered that I've actually included the solution to it, but you should, so you should do this exercise on your own. But if you get stuck, there is a solution there. in the back. But anyway, what's to the nth power? This matrix to the nth power, when applied to minus 1, 1, is going to give me this. Okay, so very, very easy to compute. Now, how about that guy, 0, 7, which was not an eigenvector? How do I compute this power of the matrix applied to a non-eigenvector? Well, the trick is to express 0, 7 as some linear combination of the eigenvectors that you know. And the eigenvectors that you know is 2, 5, and minus 1, 1, right? So 8 times that much plus maybe how about A is 1 and B is 2? Will that work? I think if you add those up, that mixture of the eigenvectors gives you exactly this vector. Well, then how do we compute the gazillionth power of matrix A applied to this vector? Well, we apply A to this vector, which is tantamount to applying A to the mixture, to the linear combination of those two vectors. And then you use matrix arithmetic, and it's easy to do this. But anyway, good exercise. You should do it. So maybe it will show up on the quizzes, but here's the answer. You should get this answer when you work this out. Now, we'd like a streamlined way of computing eigenvalues and eigenvectors. And now you may say, so here's what the problem is. Somebody gives you a matrix, A. It's like, I don't know, 3 by 3, 27 by 27 matrix, whatever. And they tell you compute its eigenvalues and eigenvectors. And you're like, well, okay, so you think about it for a second. So you know by definition what an eigenvalue and an eigenvector is. So you say, okay, so I need to find this vector V here somehow, such that when I apply A to it, it gets stretched by lambda. But then you think about this for a second, and then you're kind of perplexed a little bit because you don't know what V is. You don't know, you're asked to find eigenvectors. You also don't know what lambda is. You're also asked to find the eigenvalues. All you really know is just this guy is all you know. You don't know this guy, you don't know this guy, you don't know this guy. There are just too many unknowns, too many question marks. So how do you actually solve it? So that's what we want to do. It turns out it's not that complicated. We have to understand the procedure of why it works and then apply it. Apparently, well, it will turn out it's not going to be complicated. It's just an algorithm that we apply every time. It works. Just have to learn it. But we do need some background information. And we have to talk about the determinants, which all of you have seen somewhere in high school. If you haven't, then you have chapter 3 to read today, right? So okay, before I discuss this, can I ask you, like, did people get started on the homework assignment? Did they find it particularly exciting or super tedious, or what's the consensus on the assignment? Should we just keep the deadline as is, or what should we do? Because this is kind of background information. We want to get that chapter out of the way. It's relatively small, and this is stuff that many of you, but maybe not all, have already seen. So on the one hand, I don't want to make things more complicated than they need to be for some people, right? So if people would like a couple of extra days, we can postpone the assignment, right? Or like until this needs to be done before the break. So let's say Sunday night or something like that, right? So please,
works, yeah.
Does that make sense, right?
Okay, yes. Mm-hmm.
Yeah, it might be helpful.
Yeah, okay. Okay, so if that helps, then we should do this. But we still should talk about determinants. So I'll postpone that later. So just while we're on the subject, you'll have 2 more assignments that are automatically graded on Canvas that will be posted, right? The remaining parts of the book. But then I'll also post additional problems that you work through before the exam. Okay, so I'll post those for now without the solutions. And then when we come back, hopefully you will have worked through much of it, and then you'll be asking me questions, and then we'll talk about making solutions available to those. But I'll post like practice questions also. Now, please remind me, what is a determinant? So our goal, now keeping in mind, why do we need determinants? Well, we don't know yet. Let's just remember what those are. But keep in mind, please, that our ultimate goal is to find the eigenvalue, is to have a way of determining what the eigenvalues and eigenvectors of these matrices are. So note, in this part of the course, we're no longer, first of all, doing row operations. to matrix. Okay, so let's leave that aside. Our matrices will be squared. Our matrices, this part is about square matrices. All our matrices are now squared. Okay, so please help me out. Well, what is a determinant? You've seen, if you've seen, most of you have seen this before. What is that? And I'm not asking about the formula. If you remember a formula for a particular case, that's fine too. But what are they? What are they for? What if you had to describe it to someone who doesn't care about knowing the formula? What would it be? Okay, so determinant. A determinant. So you apparently, presumably, have some matrix A, and there is something called the determinant of a matrix. Well, what is that? Please help me out real quick so we can move on. So it's a, anyone remember before? So it's a number, right? A determinant is a number. It's a one number summary of a matrix, a kind of strength. So you have a huge matrix, it's an n by n matrix. And if somebody were to give just a one number summary of this entire giant matrix, to somehow summarize it to just one number, they would give you the determinant of that matrix. Okay, so what does that mean? All of that verbiage? That means that a determinant is a function that associates to the set of matrices, it associates some real number to the set of matrices. So this is matrices, Mets. So in particular, let's say for A that belongs to the set of matrices, that of A is some number, right? Determinant of A is some number. So that's the point. It associates a number with a matrix. But what does that number stand for? That's what I'm asking, I guess. What is that number? What is the meaning of that number? And we'll be asking how to compute this, and we'll have a formula. And I will not be asking people to memorize that formula, although you should. It's easy to remember that formula in a 2 by 2 and 3 by 3 cases. And there is a mnemonic for it, but I'm not asking you to memorize it. Just want people to know what determinant is for, at least partly. And yeah, you can always write this down on a sheet of paper. You're allowed to have a cheat sheet. So you write down the formula if you'd like to, because in a couple of cases you need to compute the determinant of a matrix, 2 by 2 or 3 by 3 matrix. And it's nice to have a formula handy if you'd like, but we need to know what it stands for. Okay. Well, we think of a determinant. Well, let's take a matrix A, B, C, D here. Again, there is some formula that computes it, and here's the formula. And okay, that's fine, but what does it do? Consider a concrete example for the time being. So let A, B, C, D be this matrix, 2, 4, 3, 1. And take these columns of this matrix, view them as vectors in their column space, and draw them as vectors. Now notice, so I'm not looking at this matrix now as a transformation. It can be viewed as a linear transformation. It represents some linear transformation. That's fine. But I'm just, at the moment, I'm just simplifying my view of this matrix considerably. I'm just looking at its columns and just drawing the columns. When you draw the columns, here's my 2, 4, and here's my 3, 1. If they're not collinear, that is, if they don't point in the same direction or in completely opposite directions, that is, they don't lie in the same line, then they form a parallelogram like this, right? So I can build this kind of area on top of these two vectors. Now that area, that figure, the geometrical figure, parallelogram, has an area, right? If the two vectors are not parallel to each other. Well, that area is what the determinant measures. Now, it's a good exercise in high school geometry to actually see that the area of this parallelogram is actually 10, which happens to be 3 times 4. Here's 3 times 4. This is called the main diagonal. This is how this formula goes. So you take the guys on the main diagonal. These are A times D. And the guys on the other diagonal of this matrix, these are B times C. So when you compute A times D minus B times C, you get some number. That number is called the determinant. It's a good exercise. I'm not asking you to do this, but you should really. I mean, if you have like some time, you're traveling, maybe you're not driving, maybe you're taking a train somewhere. If you it's good to think about things like this. Well, maybe, I don't know, depends on what you like to think about, but to see why this is, why this area is exactly that, AD minus BC. So you're invited to experiment in every way that you can think about. Maybe you want to draw this like a, square here at this tip, and then maybe you want to subtract the areas of these triangles here and see what you get, and then you want, any way you'd like to do it. But when you compute the area of this parallelogram here, you will see that it's going to be exactly this number. Okay, so good exercise to prove this. We're not going to do it here. Okay. By the way, if you were to draw vectors 3, 2, and 1, 4 in another two-dimensional case, now notice what I'm doing now. If I'm looking at these rows as vectors, I'm now operating in the row space of A. So that's it's a two-dimensional space also, but it's not this space. It's a different space. This is the column space. Now in the row space, when you draw those vectors 3, 2, and 1, 4, and build a parallelogram on those two vectors, and by the way, they will not be collinear, those two vectors, certainly. When you build that parallelogram there, it may have a slightly different shape. It may be smaller, maybe elongated in one dimension, shorter in the other direction. But when you compute its area, it's also going to be 10, right? So again, the determinant measures, let's stick with the column vectors, measures the area that's spanned by the columns of this matrix. Same thing is happening in a 3x3 case. So here's a 3x3 matrix. Again, what's a determinant? It's a function that's associating to a matrix a number. So it's a mapping between the set of matrices, square matrices, to the set of numbers. What does that mean? You take a 3x3 matrix, it has some number associated with it according to some rule that is a single number. What is the rule? Well, it's the volume computation. If these three vectors are vectors that point every which way, that is, if they form a box like this in a three-dimensional case, so in this concrete example of a matrix that we take, we'll look at the columns of this matrix, and the columns happen to be these vectors. And when you draw these three vectors, they point every which way. That is, you can build a box, a parallelepiped called a box, we'll call it a box, in this three-dimensional space. It has some volume. You will have a volume unless those three vectors lie in the same plane or they're all in the same line. If you don't have that kind of case, you'll get a box. That box is called, well, the volume of that box is called, is the determinant of this matrix. Well, of course, now how do you compute this determinant of a matrix? Well, there is a formula, and here's the formula. Again, you don't have to memorize this, but it's nice to have it handy. And there's also a nice mnemonic for computing the determinant of a 3x3 matrix. So here's an example. You write down the 3x3 matrix. You want to know its determinant. And this picture here shows how to compute it. The determinant is going to be the sum of 6 entries. 1, 2, 3, 4, 5, 6. Some of these entries are positive. Some of these entries are negative. Okay, why 6? And what are the 6 entries? Well, you wrote down the matrix, then you took this column and just tacked them on here. So you've ended up with a 3x5 kind of grid of numbers. Matrix also, but let's just call it a grid of numbers. And then you go diagonal by diagonal. The first 3 diagonals here, starting from the main diagonal of the original matrix, will always go into the sum with a positive sign. This 1 times 5 times 9 goes in here with a positive sign. The next 2 diagonals, like 0 times 6 times 7, this guy goes in here with a plus sign. This goes in here with a plus sign. It's just a rule to remember. I mean, to write down, to understand and write down. Okay, but if you understand it, you'll remember it. I mean, it's difficult to forget this rule once you've just thought about it a couple of times, maybe with spaced repetition. I don't know. But anyway. Okay, so these go with the plus sign, and then the last 3 non-main diagonals slanted this way go with a minus sign. So for example, this guy, 1 times 6 times 8, 1 times 6 times 8 goes with a minus sign in here. So of these 6 terms, you have 3 with a plus sign, 3 with a minus sign. You add those up, you get some number. That number, disregarding the sign, Of course, by the way, I should have mentioned that the volume is up to the sign. So if you get the determinant to be negative, then the volume is the absolute value of the determinant, right? So 3 is the volume of this particular set of vectors, of these column vectors, right? Anyway, okay. So anyway, this determinant, that computation gives you the volume that's spanned by those 3 vectors. And the sign has to do with the orientation, the orientation of these vectors in space relative to one another, right? So there's something called the right-hand rule. We don't want to get into these details, but it's nice to know about them, but it's not very useful for us. All we care about is the computation of the determinant for the purposes of later computing eigenvalues and eigenvectors, which looks like we're not getting to today, but we'll do it on Monday. Okay, what else do I have to mention before we stop? Okay, so there's sometimes, so this formula that we just gave can be generalized. There's something called the cofactor expansion. You may have heard about it from high school. You don't have to remember that. It's not a very, well, actually, this cofactor expansion, it's not an ugly formula, but it applies, it's not, computationally, it's a huge no-no. Okay, so nobody computes determinants of the matrix, of a 100 by 100 matrix using this cofactor expansion. Okay, so there's another. So cofactor expansion would go something like this. You can expand by either a row or a column, let's say by a row. So you start by this, you scratch out this column and this row, and you're down to a smaller matrix whose determinant you can compute, presumably recursively. So you multiply this number by the determinant of this guy. Then you subtract -1 times, scratch out this column, this row. Again, you're left with a 2 by 2 matrix here, indicated by the dots, which is a smaller matrix, whose determinant you can presumably recursively compute. So you multiply that by this determinant. Then you multiply this, scratching this out, left by a 2 by 2 by this, and you add those up. So there's a formula. Again, you don't have to know it. But if you prefer to compute your determinants that way, by all means, write down anything that makes you happy, any correct way of computing these determinants, and have it. But normally, actually, you should know about this cofactor expansion, because the matrices that you will be given in quizzes will have determinants that are actually very easy to compute. Although they may look like huge 4 by 4 matrices, they will have a bunch of zeros inside of them. So many of your terms in your product, okay, this product of expansion, for example, can also be viewed. This is also a way of viewing this as a cofactor expansion. So many of these terms will be 0. So it will be, if you know how to compute this, it won't be too much trouble, right? Computational, because many of the terms will be 0. Just have to know how to compute if you have to. So please bring that on your cheat sheet. Okay, the much better approach would be to do a few of them by hand, which you should in the homework assignment, and you won't be able to forget that formula before the end of by the exam. You won't forget it. So, but you can have a cheat sheet anyway. I don't know how many. I said this like 50 times. I don't know why I'm sort of like staying in place here. We should be moving on, although we don't have much time left. The last thing, let me mention this. Sometimes a matrix may have a simple structure. Like this, an upper triangular matrix, in which case it's easy to compute the determinant, right? So you can apply your cofactor expansion, but when you do, you'll find that the answer, the determinant of this matrix, will be simply the product of these diagonal entries. So if you have a matrix like this that is up or lower triangular, okay, if it's either upper, what is a lower triangular matrix? So you have a matrix something like that. You have these entries. These are non-zero entries. The dots are non-zero entries, and everything above the dots right here, these are zeros, and everything below are not zeros, or maybe some of them may be zeros, maybe not. Right, so you have a matrix like that. Then this matrix is a lower triangular matrix. Its determinant is simply the product of the terms on the diagonal. Simply multiply these guys, and that's your determinant. So there are some special cases where it's especially easy to compute the product, the determinant of a matrix. All right. So any questions about any of this? So this computing the determinants, like this homework assignment, that's all background information. Takes n, sorry.